So that last film was a bit of a marathon, this one is not. I want to try and keep it as short and quick and simple as possible. The last time I considered the oscillator in terms of forces so that I could explain that definition of SHM in terms of acceleration. That the acceleration is proportional to displacement and always directed back towards the equilibrium position. Today I'm going to look at oscillators in terms of energy, and given what you are learning, notice not what you already know but what you are learning from the last book, hopefully this will make a lot of sense. So let's have a look at the pendulum again. If I displace the pendulum up to its amplitude point, it's gained some small amount of height. Okay, in this case it's only very small, but this is the best I've got to work with. So from the equilibrium position to the maximum displacement, there is an increase in height. So let's think about energy. At the maximum displacement, the oscillator has gravitational potential energy, has a maximum potential energy. In this case, because it's a pendulum and I've moved it upwards, it's gravitational. But just bear in mind, if this was a mass between two springs, that might be elastic potential energy. Either way, at the maximum displacement, the potential energy is a maximum. If I left the pendulum to swing, you should know by now that that pendulum will have its maximum velocity in the centre, the equilibrium position. If it has its maximum velocity there, then it doesn't take a big stretch to say it also has its maximum kinetic energy in the middle at the equilibrium position. And if you think about energy conservation, where has that kinetic energy come from? It's come from the potential. And we are ignoring energy losses here because that's for the next booklet to consider. We're just getting the basics down. If we assume that all the energy is conserved in this system, which largely it is, all of that gravitational potential from the start is transferred to the kinetic as it passes through the equilibrium position. Obviously, the oscillator will then continue on to its next maximum displacement at the opposite side, where it gains that same small change in height, leading to that same small change in GPE, which then goes back to the kinetic and back to GPE on the other side. Do you get it? So when we're considering energy in oscillators, we have to remember that at the maximum displacement, we have a maximum potential energy. And you need to name what type of energy that is. Have a look at the thing that you're given in the question. If it's a pendulum, it's probably gravitational. Is it on a spring, then it's elastic. They're usually pendulums or springs, so it's going to be gravitational or elastic. You need to know that in the centre, where it's moving fastest, it has its maximum kinetic energy. And by extension, because we're assuming that energy is completely conserved in this case, we can set those energy types equal to each other. So the maximum potential energy, let's say mg delta h in this case, is going to be equal to the maximum kinetic energy, a half mv squared. It's going to be equal to that GPE that it goes to on the other side as well. So energy in oscillators, once you get the basics from that previous marathon watch video, energy in oscillators is very, very straightforward to consider. You've got potential, some kind of energy store, kinetic to potential to kinetic to potential to kinetic. Pendulum's high up, pendulum's moving fast, pendulum's high up. I think that's fairly straightforward. So Rob, what could a question ask me about? What can I be asked to consider? Well, it's fairly straightforward. You can be asked to calculate how big the magnitude of the energy is and set them equal to each other. So they might say, the pendulum is displaced by 5 meters, its height gain is 5 meters, what is the speed at the equilibrium position? And so you just set those two energy types equal to each other and hey presto, it's done. The main thing that they ask is wordy questions asking you to describe the energy transformation. And I just did that for you then as an example. So in a pendulum, the oscillator gains height, therefore it has gravitational potential energy. But this is transferred to kinetic energy, which is at maximum at the equilibrium position, and then it also gains height as it moves away from the equilibrium position, therefore gaining gravitational potential energy again, and so on and so forth throughout the oscillation. Yeah? It's usually worth 3 or 4 marks for that kind of describe, and there's an example I think in the book. Some oscillators might be a little bit more complicated, so for example, if I had a mass on a spring, it might seem quite straightforward, but if I was hanging a mass from a spring, so it would bounce like that, you've got to bear in mind that there is 2 types of potential there. When the mass is at its highest point, it will have gravitational potential energy, and then when the mass is at the bottom of its bounce, if you like, the bottom of its spring, it will have a maximum elastic potential energy. When the mass is in the middle, it will have kinetic energy, but also some small amount of elastic potential. And I think there's a question like this came up a couple of years ago. Most of our students got 2 or 3 out of 4 marks for saying potential, kinetic, potential, but they forgot to name the types. Some of them didn't realise that there was more than one type of potential energy at play there. So just keep your wits about you when you're answering these questions. The idea isn't hard, you've just got to name the type of energy. Yes, there is one last thing in this book, and it is a graph. Just to help you explain this, I said that in this situation that we're considering now, energy is conserved. There's no friction, there's nothing acting to remove energy. And so the total energy of this oscillator at any point in its oscillation is constant. So let's start off with putting that on a graph. Let's plot a graph of energy on the y-axis and displacement on the x-axis. Remember, displacement can be positive and negative either side of the equilibrium position. The total energy is constant. What does a constant look like on a graph like this? Well, it's just a flat line. So the total energy is a straight line. Easy. Let's then think about the kinetic energy, because that's probably the easiest one to consider. The kinetic energy of an oscillator, we know, is 0 at its extremes because its velocity is 0. So we can mark on the amplitude of our oscillator just with a little cross on the 0 crossing of the energy axis, because that's where it's going to have 0 kinetic energy. We know also that the kinetic energy is maximum in the middle at the equilibrium position. So whatever our maximum kinetic energy is, put across there on the equilibrium position. Notice I've not said put across on our maximum energy line. Maybe it goes there, maybe it doesn't. It depends. And I'll talk about why in a second. But whatever your maximum kinetic energy is, let's cross it off on the line. We know that velocity varies as a sinusoidal thing, it's not a straight line. So we join those with a parabolic curve. Okay, so it's a nice parabola as drawn for you in the book. So that's all very well and good. Let's think about the potential energy now. We know that the potential energy is a maximum when the kinetic energy is 0. And we know that in order for the total energy to add up, that potential energy must be the same as the total energy at the starting point. So much like how for kinetic we drew a point on at the 0 energy line, here draw a point on that total energy line. How much potential energy is lost? Well, we know that the change in potential is the same as the maximum value of kinetic energy. So look at how high up your kinetic energy goes on the graph and use that same change in height but downwards from the top line for your potential. Now notice, in the simplest case, the maximum kinetic energy goes on the line and therefore the minimum potential energy is 0. But if there is some excess energy in the system, if there's an excess potential, then I can just raise everything up and it still makes sense. The change in kinetic energy is still the same as the change in potential energy. I know when you look at that graph as is, it's just a collection of lines and it probably doesn't make that much sense. But when you think of it as described, when you think of the total energy of it is always constant, the kinetic energy goes between 0 and maximum and 0, and so the potential energy goes between maximum, minimum and maximum. Hopefully that makes a little bit more sense as to what that kind of complicated graph is trying to show you. So that's it for energy, that's all. Done. There's one last bit that I just want to talk about, and this is the summary page for this booklet. Hopefully you've gone through and carefully filled in all the quantities. Make sure you know the difference between things like capital A and little a for amplitude or for acceleration. Make sure you know about quantities like angular frequency. Make sure you recognise how to use those sign things. I know there's a lot to take in oscillations. I didn't lie there. There is a lot of stuff. But I hope that over the course of this week it slowly starts to consolidate and make sense. Take your time with it. What I wanted to spend some time on was the two graphs on the summary page, which I don't think even have answers in the book. One of them is an acceleration displacement graph, and it's a 4-quadrant graph. The other one is a velocity displacement graph, and again it's a 4-quadrant graph. It's got the positive and the negative areas. We'll start with the acceleration one because this one is the easiest to explain and understand. This graph essentially says what is the acceleration for any given displacement of the oscillator. And if you recall, it's written above it, the definition of an oscillator is that the acceleration is proportional to the displacement but always directed back towards the equilibrium position. And it gave rise to that proportionality relationship. Do you remember? A is proportional to minus x. And it's that should tell you what to draw on this graph. It is a graph of a negative proportionality. So it's going to be a straight line, it's going to go through the origin, but it's going to have a negative gradient. And that means it goes across in the opposite direction to normal. It doesn't go up into the positive quadrant, it goes down into the negative quadrant as pictured. Remember, this graph is the easiest one to draw. It's just a straight line through the origin, but it has to have a negative gradient. The reason why is because the acceleration is proportional to minus displacement. The next graph is a bit more challenging because it relates to velocity. Now obviously, whenever you're plotting a function, you can just put in values, but what if you don't have values? How could we analyse this? Well, let's think about what we know. The velocity is 0 at the amplitude. So we can put a little cross of 0 and a little cross of 0 on either side of the amplitude, just like we did for kinetic energy. Unlike kinetic energy, velocity can be positive or negative at any displacement. Remember the equation v equals plus or minus omega square root a squared minus x squared. That tells us the velocity, it could be in the positive or it could be in the negative direction, depending on which way it was swinging. So let's go to the highest value. We know that when the displacement is 0, that's another extreme. And we know that the velocity could have a maximum positive value, which would be equal to omega a, and it will also have a maximum negative value. So it's not that it has those at the same time, because this is not a velocity time graph. This is a velocity displacement graph. It means at that middle point it could be going this way or that way with its maximum velocity. So we have to plot a point at the top on the highest velocity and the bottom. So far so good, maybe? The question then arises as to how do we link those points together? What we need to remember is that for every positive value of velocity, we can also have a negative value of velocity. We know that velocity varies sinusoidally, it's not a straight line. And actually, I mean, if you've done maths, you might be able to spot this graph actually traces out a circle. Who'd have thought it? So if I wanted to plot a graph of velocity on the y-axis and displacement on the x-axis, that graph traces out a circle. Hopefully with time, the more you understand what this graph is saying, that will make more and more sense. It's not saying that the velocity at any one time is in two directions, because that makes no sense. Remember, it's not a velocity time graph. This is a velocity displacement graph. What could the velocity be at a given displacement? And we know that where it's not zero, the velocity could be positive or negative. And that's what this graph tells you. It's really clever. So I hope that that's been handy for you and a little explanation of those things, and I hope that I've managed to keep it short as well. Again, there's not much to this section of oscillations, but there is a lot to oscillations in general, and I want you to just make sure you're consolidating. I'll say no more about it because you know how important it is. Make sure that you spend a good chunk of time getting oscillations right. It's a bit like Waves 2.0. It takes time. Be slow and be deliberate about it. It does make logical sense if you think about it, you can visualize what's going on, but sometimes, like that velocity displacement graph, it's not quite what we might have initially expected.